friends, I am Dr. Sudhan Sharma from School of Computer and Information Sciences, Indira Gandhi National Open University. And in our previous session, we learned about the concepts of functions, limits, and continuity. And it was expected that you understood the concept of limits and continuity and you solved the problems given in your self-learning material. And assuming that you had solved the problems, we are going to extend the discussion to the differentiation part. In this session, we are going to discuss about the derivatives of functions. This is the first session in the series of differentiation, that is derivatives of function. And we are going to have one more session for the discussion on the differentiation part. The objectives of today's session are in fact to understand the concept of differentiability, and after this you're supposed to apply the rules of differentiation to solve the numericals. Apart from this, we are supposed to understand how to determine the derivatives of the exponential and the logarithmic functions. So these are the contents which are supposed to be delivered in this session. So understanding differentiability, so far as the definition of the differentiable function is concerned, if function f is set to be differentiable if limit x delta x tends to 0, x plus delta x minus fx upon delta x exists. So I hope you understand that the concept of limits is now extending. We are extending it to understand the concept of differentiability. So limit, we can say limit h tends to 0, f of x plus h minus f of x upon h. If this exists, then the function is differentiable. So we need to evaluate the limits. So if this limit exists, then the derivative of the function f at x is defined, and this derivative is nothing but dy by dx, where we can say that this is equal to d of fx by dx. So if y is equal to fx, then y derivative, that is first derivative, is written by y dash is equal to dy by dx, that is equal to d of fx by dx, and derivative of fx by with respect to x is limit h tends to 0, f of x plus h minus f of x by h. If h is replaced by delta x, then you are going to have the expression dy by dx is equal to limit delta x tends to 0, f x plus delta x minus fx upon delta x, which is nothing but the first derivative. So the function is said to be differentiable in the open interval I, and there is a remark that it can be easily proved that f is differentiable at point x if f is continuous at x. So what was delivered in our earlier session, that the function should be continuous in order to be differentiable. So that's why we delivered the concept of limits and continuity, because continuity is a requirement for a function to be differentiable. So if a function is not differentiable at x, the function is not continuous at x, then the function is not differentiable at the point x. So let's try to determine the differentiation of the functions by using the fundamental definition, which is limit delta x tends to 0, fx plus delta x minus fx upon delta x. So over here, now after solving this, we are not going to use this mechanism again and again. We will solve it by using the formulas also directly. But to begin with, let fx is equal to x square, and we are supposed to differentiate it by using the definition, that is limit delta x tends to 0, fx plus delta x minus fx upon delta x, that is equal to dy by dx. So what is if fx is equal to x square, then fx plus delta x will be equal to x plus delta x square. So substituting fx plus delta x and substituting fx, you will get the expression x plus delta x square minus x square upon delta x. You know a plus b square is given by a square plus b square plus 2ab. Applying this identity, you will get x square plus delta x square plus 2x into delta x, and minus x square is carried forward to this expression. Solving the numerator part minus x square will cancel with x square. Taking delta x common from these two terms, you will get delta x into 2x plus delta x. And because delta x already exists in the denominator, so you will get delta x and this will cancel out. So turns out to be final term is 2x plus delta x. Now the definition is f dash x, that is first derivative of the function, is limit delta x tends to 0 fx plus delta x minus fx upon delta x, and this expression is solved to 2x plus delta x. So limit delta x tends to 0, applying this limit over here, you will get the answer 2x. But the direct formula, you can see that derivative of d dx of x to the power n is equal to nx to the power n minus 1. Applying this formula, you will get d dx of x square is equal to 2 into x to the power 2 minus 1, that is 2 into x. So we are going to use the formulas also, but this is the fundamental mechanism to define the derivative of a function. By using the definition, f dash x is equal to limit delta x tends to 0 fx plus delta x minus fx upon delta x. We need to solve it. There are some rules of the differentiation, that there is a constant rule. We are going to discuss these rules by proving those rules also. The first rule, the constant rule, says that the derivative of a constant is 0. That is, d dx, derivative of a constant term, is equal to 0. Because differentiation is about the rate of change, but constant is not supposed to change. So constant not supposed to change, so that means there is no variation in the constant. So that's why the differentiation of a constant is 0. That means there is no variation. So let fx is equal to c. So in order to prove this, that derivation of the differentiation of a constant is equal to 0, again let's apply this definition, that is limit delta x tends to 0 fx plus delta x minus fx upon delta x. Now because the function fx is nothing but constant, so fx plus delta x will also be constant. There is no variation. So that's why fx plus delta x minus fx will turn out to be c minus c, that turns out to be 0. So therefore fx plus delta x minus fx upon delta x will turn out to be 0 only. So that means differentiation limit delta x tends to 0 when function fx is constant, that turns out to be 0. So that differentiation of a constant is 0, you need to remember it. Second is scalar multiple. So if we are having a function c multiplied by a function fx, then the differentiation d dx of c of fx is equal to c of d dx of fx. That so the constant part will come out. So that means we can say that c differentiation of c fx is equal to c of f dash x, that is c into dfx by dx. We are writing d of fx by dx as nothing but f dash, that is derivative, first derivative. So how to prove this? In order to prove this, let's again apply the same fundamental definition, that is we need to prove limit x tends to 0 fx plus delta x minus fx upon delta x. So what is fx over here? It is constant times. So fx is say c of gx. So fx plus delta x will be equal to say c of gx plus delta x. So fx plus delta x minus fx upon delta x will turn out to be c times of gx plus delta x minus c times of gx upon delta x. Limit delta x tends to 0. Taking c as common, you will find that limit delta x tends to 0, gx plus delta x minus gx upon delta x, and which is nothing but derivative of x. So we had proved that c times of f dash x. So d dx of c times of fx is equal to c times of f dash x. I hope you understood how we prove the scalar multiple rule. Similarly, we are having the another rule, that is sum and difference rule. The sum rule says that d dx of fx plus gx is equal to d dx of fx plus d dx of gx. So d dx of fx plus gx is nothing but equal to d dx of fx plus d dx of gx. So similarly, we are going to have the difference rule, that is d dx of fx minus gx. Fx minus gx is nothing but equal to d dx of fx minus d dx of gx. So d dx of fx is nothing but f dash x, and d dx of gx is nothing but g dash x. So this is all defined over here. Now in order to prove this, let's apply the fundamental definition again. What the fundamental definition was, that dy by dx or d dx of fx is nothing but limit delta x tends to 0 fx plus delta x minus fx upon delta x. So over here we are given fx plus gx. So we are going to apply this definition, limit delta x tends to 0 fx plus delta x plus gx minus fx plus gx. So we are simply applying this fx plus delta x minus fx upon delta x, limit delta x tends to 0. Just by applying it to this function, this complete function, what this complete function will transform, will transform to fx plus delta x plus gx plus delta x. This part minus fx plus gx. So this is what is written over here, fx plus delta x plus gx minus fx plus gx. Now segregating, taking fx terms common and gx term common on the separate side, you will get fx plus delta x minus fx, gx plus delta x minus gx. Plus sign will be common over there, and separating the limits, because we learned that limit x tends to a or x tends to 0, fx plus gx is nothing but, there was a property we discussed in the last session, is equal to limit x tends to a fx plus limit x tends to a gx. This was the property we discussed. Applying that property over here, you will get limit x tends to 0 fx plus delta x minus fx upon delta x plus limit x delta x tends to 0 gx plus delta x minus gx upon delta x, which turns out to be g dash x and f dash x. So this is f dash x and this is g dash x. On the same lines, we can prove for the difference of the rules, that is d dx of fx minus gx is equal to f dash x minus g dash x. Now there is an important rule, that is the product rule, which product rule says that d dx of fx into gx is fx into g dash x plus gx into f dash x. On the same lines, just we are substituting the function values in the very elementary formula, that is fx plus delta x minus fx upon delta x. By substituting the value, that is fx into gx for the value x plus delta x, you will get fx plus delta x into gx plus delta x. Similarly, for the value x, you will get it equal to fx into gx. So this is all we get is fx plus delta x into gx plus delta x minus fx into gx by delta x. Now adding and subtracting fx plus delta x into gx, that is subtracting and adding, you will get fx plus delta x into gx. These two terms are added and subtracted into this expression, that is expression given in equation number 1. So by adding and subtracting, taking fx plus delta x common from the first two terms and taking gx as common from these next two terms, it solves to fx plus delta x into gx plus delta x minus gx upon delta x. And because gx is taken as common, The remaining terms are g fx plus delta x minus fx upon delta x. Again, spreading the limits across the expression, you will get the expression in this form, that limit delta x tends to 0, fx plus delta x into limit x tends to 0, gx plus delta x minus gx upon delta x plus gx into limit delta x tends to 0, fx plus delta x minus fx upon delta x. So, this turns out to be f dash x, this turns out to be g dash x, and this turns out to be only fx. So, we got the formula fx into g dash x plus gx into f dash x, and this is nothing but your product rule, which says that ddx of fx into gx is nothing but equal to fx into g dash x plus gx into f dash x. I hope you understood that how to prove the product rule. On the same lines, we are having a power rule, which we had discussed in when we were solving our very first example, where we had solved x square. So, ddx of x square was computed only on the basis of this formula, that is 2 into x to the power 2 minus 1, and that turns out to 2x. The power rule says that ddx of x to the power n is nothing but nx to the power n minus 1. So, for n is equal to 1, what this ddx of x to the power n turns out to be, when n is equal to 1, this is turns out to be ddx of x. So, ddx of x is equivalent to limit delta x tends to 0, fx plus delta x minus fx upon delta x. Because fx is only x, so fx plus delta x turns out to be x plus delta x only, and only fx turns out to be x only divided by delta x. So, x and x will cancel out, and delta x and delta x also will cancel out. So, the answer turns out to be 1. For better understanding, let me solve it for you again. Now, for n is equal to 1, fx is equal to x to the power n turns out to be x to the power 1 is equal to x only. So, that is why fx plus delta x turns out to be x plus delta x. So, therefore, fx plus delta x minus fx upon delta x limit delta x tends to 0 is nothing but dfx by dx. This turns out to be x plus delta x minus x by delta x limit delta x tends to 0. Solving the expression, x cancels out by this, you will get delta x by delta x, which again cancels out, and you will get the answer equal to 1. So, when n is greater than 1, then ddx of x to the power n turns out to be limit x tends to 0, x plus delta x to the power n minus x to the power n upon delta x. Now, expanding x plus delta x to the power n by binomial expansion, you will get this expression, and applying the limit delta x tends to 0, all these values wherein delta x component is there, they will turn out to be 0, and what is remaining is only nx to the power n minus 1. Hence, ddx of x to the power n turns out to be nx to the power n minus 1 only. So, this is the power formula, power rule. There is one more rule, that is the reciprocal rule, which says that ddx of 1 by fx is equal to minus of f dash x by fx square. So, this is very important formula, this is very important formula. So, you need to remember this, and let us prove this formula, that ddx of 1 by fx. So, applying the standard definition, delta x tends to 0, fx plus delta x, fx plus delta x minus fx by delta x is nothing but dfx by dx, that is equal to f dash x. Applying this definition to the function given over here, the function given over here is 1 over fx. So, 1 over fx plus delta x will be the x plus delta x term, substituting the values over here into the same expression. Let me solve it for your better understanding. So, we are supposed to find ddx of 1 over fx. So, we are supposed to calculate fx plus delta x minus fx by delta x. So, fx plus delta x will turn out to be 1 over fx plus delta x, and fx will turn out to be minus 1 over fx. So, these terms are to be divided by the new delta x. This delta x will appear over here. So, the entire expression turns out to be 1 over delta x into 1 over fx plus delta x minus 1 over fx. Now, taking the LCM and solving, you will get this expression, that is fx minus the fx minus fx plus delta x upon fx plus delta x into fx into 1 by delta x. Taking the minus sign common, from the denominator, from the numerator, you will get the fundamental expression, that is fx plus delta x minus fx upon delta x. And this expression is nothing but your first derivative f dash x. And on the right hand side, what is remaining in the denominator is fx plus delta x into fx. So, taking the limit delta x tends to 0, you will get the answer, that is a minus of f dash x upon fx square. So, let me solve it for you. So, is equal to, this will turn out to be fx plus delta x into fx. So, this will turn out to be fx minus fx plus delta x, and into 1 over delta x is remaining. So, taking minus sign common from the numerator, numerator, you will get minus of fx plus delta x minus fx and divided by delta x into what terms are remaining, these two terms are remaining, into 1 over fx plus delta x into fx. So, we got this expression. Now, directly applying the definition, the fundamental definition, this expression turns out to be f dash x, and these two terms, because delta x tends to 0, it will turn out to be fx square. So, overall we got the formula minus of f dash x upon fx square. So, ddx of 1 over fx is equal to minus of f dash x upon fx square. On the same lines, we are having the quotient rule. The quotient rule says that ddx of fx by gx is equal to gx into ddx of fx minus fx into ddx of gx divided by gx square. Applying the product rule and the reciprocal rule and following the steps which were discussed till this moment in this session, you will be able to prove this. So, this is left as an exercise, you just try these steps. Applying the product rule, what you will get, for the sake of simplicity, let me again solve it for you. Say ddx of fx by gx will be equivalent to ddx of fx into 1 by gx. So, applying the product rule, so what product rule says that fx into ddx of gx. So, first function, so we are given, say, ddx of fx into gx, we need to find this. So, first function into g dash x plus gx into f dash x. This is what the product rule is. So, we applied the product rule and we got 1 by gx into ddx of fx plus fx into ddx of 1 by gx. Just now we found that ddx of 1 by fx is minus f dash x upon fx square. So, applying this identity, that is the reciprocal rule, we got that expression is minus g dash x upon gx square. So, solving this expression, After application of the product rule and the reciprocal rule, you will get the expression that ddx of fx by gx is gx into ddx of fx minus fx into ddx of gx by gx square. So these are some of the fundamental rules. Now let's apply these rules to solve some of the numericals. Now the first question is y is equal to, we are supposed to find the derivatives of the following function. Y is equal to 2 into x to the power 5 minus 3x. So dy by dx will be ddx of 2 into x to the power 5 minus 3x. So applying the formula ddx of constant into fx is equal to constant time of ddx of fx. So this is constant time of fx. The constant of ddx times of fx. Now we are having the power rule also, that ddx of x to the power n is nx to the power n minus 1. Applying this to ddx of x to the power 5, you will get 5 into x to the power 4. So for the first term, we got the answer that 2 into 5 into x to the power 4. Similarly, ddx of 3 into x is constant. By applying this identity, constant is taken out, so 3 is taken out, so ddx of x. Applying again this formula, ddx of x is x nx to the power n minus 1, so 1 into x to the power 1 minus 1, that turns out to be 1. So applying these two identities, you got the expression 3 into 1. So 2 into 5, that is 10, x to the power 4 minus 3 is the solution for the first question, when y is equal to 2x to the power 5 minus 3x, then dy by dx is nothing but 10x to the power 4 minus 3. You will be able to perform this in the faster manner if you are going to practicize, and if you are going to memorize the formulas which are discussed, which are proved in this session till the moment. We are just applying those formulas, and let's solve the next numerical. Now 1 over x square plus 3. So what type of function it is? It is 1 over fx. So ddx of 1 over fx is to be found. So what the formula was? Formula was minus of f dash x upon fx square. So this is the formula, that is a reciprocal rule. So ddx of x square plus 3 upon x square plus 3 square will be there. So ddx of x square plus 3, what will be ddx of x square plus 3? X square plus 3. Now you will say that ddx of x square plus ddx of 3. Now this is ddx of constant is 0, and by applying the power rule, ddx of x square will turn out to be 2x only. So this will be minus 2x, because minus sign is outside in this formula, minus sign is there. So minus 2x upon x square plus 3 whole square will be the answer for dy by dx. So we solved the second numerical also by applying the rules of the differentiation. Now the third question is y is equal to x upon x plus 2. Now applying the quotient rule, the quotient rule is ddx of fx by gx is gx into ddx of fx minus fx into ddx of gx by gx square. Applying the formula, what is gx over here? Gx over here is x plus 2. So x plus 2 into ddx of x minus x into ddx of x plus 2 upon x plus 2 whole square. Now ddx of x will turn out to be 1, and ddx of x plus 2 will also turn out to be 1. How? Why? ddx of x plus 2 will turn out to be ddx of x plus ddx of constant 2. ddx of constant is 0, and ddx of x is turn out to be 1 by applying the power rule. So you will get the answer x plus 2 minus x. So x will cancel out. So what you are remaining with is 2 in the numerator. So 2 upon 2x plus 2 square will be the solution. Again applying the quotient rule to this formula, to this question, that is y is equal to x square upon x square minus 5, you will get the answer minus 10x upon x square minus 5 whole square. Again, I recommend you to solve more and more numericals given into a self-learning material for the better understanding. Now I extend our discussion of this session to determine the derivative of the exponential and the logarithmic functions. In order to determine the derivatives of the exponential and the logarithmic functions, that is e to the power x, and natural logarithm, that is ln of x, we are supposed to remember these two important limits. What these limits are all about, that limit delta x tends to 0, e to the power x minus 1 upon x is equal to 1. And second important expression is limit delta x tends to 0, natural logarithm of 1 plus x upon x is equal to 1. So on the simple lines, we can say that ddx of e to the power x is equal to e to the power x, and ddx of a to the power x is a to the power x of natural logarithm of a. So this is also a very important formula. This is also a very important formula, and we are going to use these formulas. But before going for the solution, let's prove this formula, that ddx of e to the power x is nothing but e to the power x. Again, applying the formula dy by dx or ddx of fx is nothing but of fx plus delta x minus fx upon delta x limit delta x tends to 0 is nothing but dfx by dx. Applying this understanding, applying this fundamental formula, concept of limits, which we had discussed in our earlier session, we got that ddx of e to the power x turns out to be limit delta x tends to 0, e to the power x plus delta x minus e to the power x upon delta x. Solving for the numerator, we will get limit delta x tends to 0, e to the power x, e to the power delta x minus 1 upon delta x. Now taking e to the power x as a constant as a common part, e to the power x limit delta x tend to 0, e to the power delta x minus 1 upon delta x. What was the limit we had discussed in our earlier slide is limit delta x tends to 0, e to the power x minus 1 upon x is equal to 1. So this turns out to be 1. Hence the final solution is e to the power x. So that's why hence we had proved that ddx of e to the power x is nothing but e to the power x. But there is an important identity, that ddx of a to the power x, constant to the power x, is a to the power x into natural logarithm of a. On the same lines, we are having another important expression, that ddx of natural logarithm, that is ddx of n ln x is nothing but 1 over x, and x should be greater than 0. Applying the same concept, that is ddx of fx is limit delta x tends to 0, fx plus delta x minus fx upon delta x, and using this identity, that is limit delta x tends to 0, natural logarithm of 1 plus x by x is equal to 1, we can prove that it is equal to 1 by x. So this is a very important proof, and this is a corollary, that ddx of log to the base ax is nothing but 1 by x of log to the base a of e. So this is also a very important expression, and this is also an important identity. We are going to use these expressions, formulas, in our subsequent problems. Now there is an example, let's solve it for the better understanding. Find the derivative of the following functions, and one of the function is x square into e to the power x, and second is natural logarithm of x divided by x. Applying the product rule, so ddx of x square into e to the power x, applying the product rule, that is what product rule was? The product rule was ddx of fx into gx is nothing but fx into g dash x plus gx into f dash x. So say e to the power x into derivative of x square, e to the power x into derivative of x square, plus x square into derivative of e to the power x. What is the derivative of e to the power x? Is nothing but e to the power x. And what is the derivative of x square? Is nothing by applying the power rule, is 2 to the power 2 into x. So the overall solution turns out to be 2x into e to the power x plus x square into e to the power x. Taking e to the power x as common, the overall solution turns out to be 2x plus x square into e to the power x. Now let's solve the other question given to us. The other question given to us is nothing but natural logarithm of x divided by x. Since division is existing over here, we are supposed to apply the quotient rule. What quotient rule says? That d dx of fx by gx is equal to gx into f dash x minus fx into g dash x upon gx square. So what is gx? Gx is x over here and fx is natural logarithm fx over here. So gx, that is x into d dx of natural logarithm, minus fx into g dash x, that is d dx of x, upon gx square. So d dx of natural logarithm x is 1 by x and d dx of x is 1. So substituting the values over here, you will get x into 1 by x minus natural logarithm of x into 1. So x cancels with x. So you will get 1 minus natural logarithm of x divided by x square. Once again, I reiterate that practice more and more numericals by going through the concepts which are delivered in this session, so as to have better understanding of the concepts. This will help you out to solve ample number of questions which are to be asked from you in your assignments, in your examinations, and these are very important topics and very simple they are also, provided you remember the formulas, you remember the procedure, how to solve them. And this is all about this session. We are going to discuss more differentiation in our subsequent session. Thank you.